You do have orgo? All right. Hey, it's a hexagon with carbon.
Wish it was that easy.
What else can it do? It's a hexagon with carbon. All right. That's all I know about it. Okay. And yeah, that's it. That's all I know. But I do know about linear momentum. And here's the deal with linear momentum. It's this, that I have a collision. All right, I have a velocity, a mass times a velocity before something happens. There's a collision. And what we mean by a collision is there's two kinds. There's a collision just like any force. There's a collision at a distance, and there's collision by contact. Collision by contact we talked about was hitting a softball. All right? But the bat and the ball have a very short duration. Okay? That's what we mean by a collision, when two things smack into each other and they have a short duration that they're in contact. All right? And short duration can be defined from 0.00001 milliseconds to maybe 0.1 seconds. Okay? So, or maybe a second, but for the most part it'll be less than a second. And then there's collisions at a distance, and that would be like Halley's Comet. Comes zipping across the Earth's sky. The Earth is pretty massive compared to Halley's Comet, and so it bends its projectile just a little bit, and so it keeps going in its hyperbolic path. But the Earth made it change its velocity over a very short length of time, because right now the Moon is circling the Earth, and the Earth is making the Moon change its velocity all the time. It's going in uniform motion, but it's changing its velocity. But that's a very long duration. It's been happening for epochs, I guess, or whatever. And the Moon is still there, and it hasn't taken off. So it's a short duration. So I was talking with Dr. Roble and on how to explain this the best way about these sums of forces equaling zero, and he said, they really don't. The sums of the forces really don't equal zero. But here's what happens. All right, here's the bat. We're looking straight onto the bat here, okay, and we'll hollow it out here a little bit. We'll cork the bat. All right, and here's the ball. Here it's hitting the ball. Okay, smack. There's some sound waves coming off. Smack. Now, what's going on is the bat is putting a tremendous force on the ball like this. The ball is equal and opposite, Newton's third law, going this way. Those forces are pretty big, and this force and this force, what do they add up to? Zero, because they're equal and opposite. But we also have this little bit of force here. We and we. That's gravity. That's the force of gravity compared to these two forces. All right? So we ignore it. All right? Now, the other way, and I think I explained it, really the way to think about this thing is that if you're in deep dark space and you have a velocity, okay, and you're cruising along at a velocity and you happen to smack into somebody else who has a constant velocity, then the momentum of that system, of that two-body system before, is going to equal the momentum afterwards. All right? Okay. So let's go ahead and go to the ugly problem real quick. Let's get it out of the way. I'm not going to work it all out because I kind of got into it in the previous class, and my head started to hurt. But we have that 30-kilogram bullet, I think, and basically what we've got is this. We've got the P before is going to equal the momentum after. The momentum after. And the momentum is created by an impulse, which is a force, which is a strong average force given over a short amount of time. All right? And so we got the P before. And in this one, we've got the mass of the bullet times 400 meters per second. That's our P naught. Equals, I think we had the mass of the bullet times 100 meters per second times the cosine of 30. Oh, cosine of 30. All right, because what happened is the bullet came in, hit the block, the bullet glanced off this way, A big chunk of the block went this way at 5 meters per second. A big chunk, we'll say this big chunk like this. And then a littler chunk went like this at some angle theta. And this big chunk had 0.75 kilograms, and this little chunk was 0.25 kilograms. And we don't know the angle, and we don't know its velocity of the second chunk. And we got to find the angle. That's what they want us to do. Well, we need two equations and two unknowns. We need two equations because I have two unknowns. I've got this angle theta, and I've got this velocity I don't know. But anyway, the before equals the after. But it's also the before in the x direction equals the after in the x direction, and also the before. We got to break it down to its components. So in the x direction, the bullet started off going 400 meters per second. Is only 30 grams, 0.03 kilograms. Plus, it hits the big block, which is 0.75 kilograms, times 5 meters per second. Plus, it hits that small one, which would be 0.25 kilograms, times some velocity 2 in the x direction, which we define as the sine of theta. So here we go. Here is where, so we know this number, we know all this numbers, we can compute all this, we can compute all that, but we're stuck because they didn't give us an angle and they didn't give us that. So we're stuck with that guy. All right? So your algebra in this is just fraught with peril. You can just make all kinds of mistakes all over the place. You have the idea down. This is pretty straightforward. The momentum before equals the momentum after. That's all pretty straightforward. But the devil's in the details and in the algebra. Okay? All right? So now, this is all the x direction. This is p naught in the x. That's what we're doing here. Now let's look at p in the y. What's the initial momentum in the y direction? Thinking about the problem. Remember, we've got this bullet going straight in the x direction over here. So what's the momentum in the y direction? Exactly. Yes. It is 0. 0. Okay? And so that will, and when that's over, then that will be the mass of the bullet times 100 meters per second times the sine of 30, because that's its component, plus, what about the second mass? Is it doing anything in the y direction after the explosion? That big lunky second mass? No. It's just staying right there. So it's just going, so plus 0 for him, plus 0.25. Well, let's make it minus, because they tipped us off that it was going negative. So let's just say it's going minus this way, sine theta. 0.25 V2F. Oh, whoa! Y'all let me get away with murder here. That shouldn't be cosine theta. This is sine theta. That's the sine theta. There we go. All right. So I can get a number here and divide by 0.25 sine theta. So basically I get this. I get this number, whatever that is. I think I got to log in and everything. I don't want to waste my time doing that. Oh, the computer's not even on. How did you do this? Did you turn this off? No. Okay. All right. Yeah, the second lieutenant salute. Okay. All right. Now, got the 0.25 V2F sine theta equals m of the bullet times 100 meters per second sine of 30. And so V2F equals this mass of the bullet 100 meters per times 100 meters per second times the sine of 30. Now watch this. Divided by 0.25 times the sine of theta. So you're going to take all this guy and plug him in to this equation. I'm not going to do that. Okay? That just shows you there is a way to do it. There's a method to the madness, but we're not going to bother to go ahead and work all that out because it now just becomes stamp collecting. It's not science anymore, really. Okay, it's just an algebraic exercise. All right. Okay, so we understand. Let's back up completely. We've got force. This average force, this times some little bitty time, is equal to the impulse. And the impulse, what the impulse does is change the momentum of a system. And the momentum of a system before equals the momentum of a system after. Now, there's two kinds of collisions that we're going to worry about. There's inelastic. I wish they'd come up with something different besides in the English, besides inelastic and elastic. All right, there's inelastic, which I'll write on the board. And I'll do these two examples. We've got inelastic collision and elastic collisions. Inelastic stick together. In other words, before the collision, I've got an M1, V1, and an M2, V2. But after the collision, I've got M1 plus M2 times some velocity. They've stuck together. Okay? They have stuck together. All right? Now, that's inelastic. Now, in an inelastic collision, that's like when you dent your car. Two cars kind of have a little fender bender in a parking lot. They stick together, right? Kind of bonk, stick together. But what happens is, because of that denting and that sticking together and stuff like that, you lose a lot of energy. And so the kinetic energy in an inelastic situation, the kinetic energy before is greater than the kinetic energy afterwards. So if I looked at the total kinetic energy of the system, it wouldn't be the same. Yes?
On the velocity on the after part of it,
Uh-huh.
do you add those two, or I mean, how do you find that? Because you've added the masses, but then there's just this V there.
Right. So think about it. They're stuck together. So the velocity is the same for both of them. They're stuck together. If you and I are hooked together or in the same car, traveling, aren't we traveling at the same velocity? We're the same thing now. So basically, you know, if I throw something like, let's say, two pieces of putty smack into each other in space and they stick together, then they're both going to go with the same velocity in the same direction. But their masses are now added together. Okay? We'll look at an example of that. And then we also have now, we have perfect elastic conditions, collisions, okay? Perfectly elastic collisions, the only perfectly elastic collisions actually occur at the atomic level. Electrons bouncing off each other, those kinds of things. But there's some things that come pretty close. Two ball bearings smacking into each other kind of create elastic conditions, okay? So in elastic collisions, before I go any further. Linear momentum, which is what we're talking about here, is still conserved. Linear momentum is still conserved even in inelastic collisions. Okay. Elastic collisions, we've got M1 V1 plus M2 V2, and there could be a bunch of them. Initial is equal to M1 V1 final plus M1 or M2 V2 final. All that stuff. Linear momentum's conserved. But their kinetic energies before equals the kinetic energy after. Ooh, final. Equals the kinetic energy at the end. Okay? And, of course, the linear momentum before is equal to the linear momentum afterwards. All right. All right. Now, let's look at a completely elastic condition. All right? Collision. I keep saying condition. Let's look at a completely inelastic collision. That's on page 198. We're going to be looking at this guy. All right? And they actually throw out some equations that we might need. All right? But anyway, what we have is we've got a 1 kilogram ball with a speed of 4.5 meters per second. Rolls along, and it hits a 2 kilogram ball, and they roll along together. Okay? So you might be going, what? What's causing that? So you got a 1 kilogram ball. It's rolling along, and then it strikes this 2 kilogram ball that's at rest, and then they kind of just go rolling along together like this. You might be going, well, wait a minute. Why isn't this 1 kilogram ball shooting off that way? Well, because, yeah, the 2 kilogram ball is creating a force that way, but it probably wasn't a strong enough acceleration to slow it, to bring it to a stop, or to reverse its velocity. Okay? Do you think it'll be going slower? Yeah, it'll be going quite a bit slower. Okay. All right, so this was not too bad, because the initial velocity of the first one is 4.5 meters per second. The velocity of the second one is equal to 0. So the P coming in is equal to P final, and so you wind up with M1 V1 naught equals M1 plus M2 V final. Okay? So this would be 1 times 4.5 equals 1 plus 2, 3 kilograms, times V final. So you've got 3 divided by 4.5 divided by 3, which equals 1.5 meters per second, which meets our, that's in our wheelhouse pretty good. We understand that. We get that. It's probably going 1.5 meters per second. Now, here's a classic inelastic collision. Okay? Did I talk about the, yes, Mary?
I'm sorry, I missed where did the 1 come from? I thought we just said
It's a 1 kilogram thing.
Okay, I'm sorry.
That's okay. I didn't put the units. You should be confused. All right? My mistake. All right. Now, did I talk about the shopping cart and cases of beer? Or, well, Diet Dr. Pepper or whatever? Okay, say you're planning a road trip. All right? You want 2 cases of Diet Dr. Pepper. I've never had it. I like their commercials, though. But anyway, all right. You got 2 cases of Diet Dr. Pepper. and your buddy pushes the shopping cart, nice vertical velocity coming at you, and it's got a certain mass. Let's say it's got a mass of 15 kilograms. That'd be about right for a shopping cart. Yeah, it's probably right around there. 15 kilograms coming at you, and you got your 2 cases of pop, and you drop them in there. Bang. And that shopping cart is going, let's say 4 meters per second. And you drop these, well, cases of pop are heavy, aren't they? They probably weigh 10 pounds. We could figure it out. A gallon is, I don't want to go through that. Anyway, they're heavy. Boom, you drop them in there. All right. What happens to the shopping cart? Does it speed up, slow down, or stay the same speed? It'll slow down because it's an inelastic. It's just like this. It's an inelastic collision. Now you might be thinking, hey, wait a minute. You told me that the sum of the forces is equal to 0 when the sum of the forces is equal to 0. Well, let's think about that for a minute. In fact, let's see what happens when we've got a 15 kilogram shopping cart, because this is a good problem. In fact, on your test, expect to have a boat cruising along and Batman's going to jump off a bridge into the back of the boat of the bad guy. It's a classic problem that I like to give. But anyway, this is the same idea. So you might be thinking, hey, wait a minute. If I've got a shopping cart moving along with a mass of, here's my shopping cart. Okay? Here's my shopping cart. And it's moving along, and it's got a mass of 15 kilograms. And and mass 2 is the cases of beer that are Dr. Pepper. Sorry. 2 cases of Dr. Pepper I'm going to drop in there. And we're going to say that they're 10 kilograms for both of them, 5 kilograms each. That'll be about right, about 10 pounds each or so, roughly. All right? Bang! They fall in there. And the shopping cart had a V naught of 5 meters, let's say 5 meters per second. What's its velocity? What's its final velocity? Well, it's the same thing as over here. Basically, we've got m1 times 5 equals 15 plus 10 times VF. So we've got, what was it, 75 kilograms meters per second equals 25 VF. So VF equals 3 meters per second. Now, you might be going, hey, wait a minute. You dropped these guys. They had a y component. So shouldn't the p in the y direction initially equal the p final in the y direction? Shouldn't it? And these guys you dropped them. And so right before they hit the cart, they had a velocity going down into this cart. Aha! If you thought of about that, which you probably didn't, but I'm telling you to think about it, this is not true, because what's the final velocity in the y direction? 0. This is not true. Well, something's going on. And the something that's going on is we're introducing a force here. Now we've got a different force. Before the only force that was acting on these guys was mg pulling it down. Okay? Now you've got it, when it hits the cart, it's got an mg and a normal force. So therefore, all bets are off. It's not, y is not conserved. But the x component is conserved, because there's the only other, we're going to say all things being equal, there is friction, of course, on the floor that would also add to the slowing down. So if you did an experiment, if you're in lab, and they said, what's the error? You'd say, well, there's probably some slowing down also due to friction and stuff like that. Okay? But which is really where science takes place. If you want to, science is in the air. Okay? That's where, for some reason, okay, editorial comment here. Here's 2 minutes of your life you're not going to get back. That has nothing to do with physics. But anyway, I think we do a bad job in our public schools of teaching you that the right answer is where you want to go, and that there's a way to get to the right answer. We should be teaching you the process is the way to go, or what are the possibilities and things like that, instead of always just looking for the right answer. And so that's what you're doing in lab when you're trying to find those errors. You're looking at, you're thinking, trying to think creatively and figuring out, just throwing all kinds of ideas out there. Well, what else would make the cart slow down? You know, there's bumps in the tile. There's all kinds of places where it could lose energy, things like that. Anyway, so all right, I'll get off my soapbox now of just looking for the answer. All right, now, so anyway, we found the VF, but this is why. But the P naught in the x direction does equal the PF in the x direction. However, the kinetic energies are not the same at all. The kinetic energies are not the same at all. This one has a kinetic energy of 1/2 of 15 times 25, which is 15 times 12.5. I don't know what that is off the top of my head. Whereas this one has a kinetic energy of 1/2 of 25 times 9, which is 12.5 times 9, which is bigger. This guy, by quite a bit. It's 12.5 times 15, whereas this one is 12.5 times 9. It just was lucky that one happened to be the square. The 25 was the square of the velocity on the one, and the other happened to be the two things added up. And so actually the ratio, always, the ratio in a problem of just two masses of the kinetic energy final over the kinetic energy initial is always going to be M1 over M1 plus M2. It works out that way every time. That's an inelastic collision. Elastic collision, all bets are off on that. Because kinetic energy is preserved, conserved, whatever, is the same before and after in an elastic collision. Now let's take a look at an elastic collision real quick. I'd made one up in the other class, and that was probably a bad idea. I shouldn't have done that. You should always stick with the book, okay? An elastic collision, let's take a conservation of momentum and kinetic energy, all right? It says this. I've got a ball with a speed of 0.3 kilogram ball. Now we're going to look at elastic. Remember, linear momentum's conserved in both situations, but only in the elastic collisions is the kinetic energy also conserved. Okay, I got a 0.3 kilogram ball with a speed of 2 meters per second. Mass equals 0.3 kilograms, mass 1, and a velocity of 3 meters per second or 2? 2 meters per second. That's its initial velocity. It's going to smack into, in the positive x direction, it has a head-on collision with a stationary mass 2 with a stationary ball of what kind of mass? 0.7 kilogram. Oh, a big old 7 kilogram mass, and its initial velocity was 0. What are the two velocities of the ball after the collision? That's 0.7. It's not quite that much bigger. It's not 21 times bigger, but we're going to look at an extreme situation here in a minute. Now, this just gets ugly beyond belief if we actually did this thing. Because look what happened. Let me at least get it started. We got 0.3 kilograms times 2 meters per second plus 0.7 kilograms times 0. Well, that's kind of so far. Now, this is going to equal 0.3 times V1 final plus 0.7 times V2 final. Uh-oh, how many unknowns do I have here? 2. But it's an elastic collision, so what else can I throw in there? Elastic collision means what? Kinetic energies are equal, right? So, I could throw in this bad bear. 1/2, 0.3 times 2 squared plus 0.7, well, this is just 0, equals 1/2 times 0.3 times V1 final squared plus 1/2, 0.7 times V2 final squared. Now I've got another equation. Now I've got 2 equations, 2 unknowns. You think the algebra on this is this beyond ugly? Yes?
And we can use the kinetic equation because it's conserved. That's why?
Exactly, because it's an elastic collision. That's the big difference. You can use the kinetic equation. You know what I like to do instead? I like to go to my book and look up something that's already been done. That's the preferred method for me, because I'm lazy. So I go, oh, you gave me a cool formula. My V1 final this is only for elastic. Well, inelastic's not that bad because we only wind up with one unknown anyway at the end, because they're all stuck together. So it's fine if we know the initial velocity is going in. This only works for elastic collision. So here we go. And then we'll talk about a certain situation here in a minute. Equals M1 minus M2. So V1 final divided by M1 plus M2 times V1 naught plus 2M2 over M1 plus M2 times V2 naught. Kind of ran it out of room there. Here's that half. Aren't you glad we didn't derive all that? And then V2 final is equal to this. 2M1 over M1 plus M2 times V1 final minus M1 minus M2 over M1 plus M2 V2 final. Now, in our situation, what was the V2 initial? What was the initial velocity? That second ball was just sitting there, right? Yeah, it was just 0. So these two guys, if V2 is equal to 0, then you don't need these two guys. Wow. That was fun. Okay, now, so that's the way you'd go about finding it, and the rest is just plugging in and making sure you work your calculator correctly. Okay? All right, now, let's take a look at a kind of a unique situation here. Let's take a look at the situation. The book kind of goes into this a little bit. Unique situation where M1 is a lot less massive than M2. So here's the situation. I got an elephant. Okay? I'm going to take this elephant. I'm going to put him on a hockey rink at center ice. Okay? And from the goal, oh, and on this elephant, on his little toenails, I'm going to put catcher shin guards. Okay? So this elephant has these little catchers, so it's going to be a completely elastic collision. All right? Now, from the goal, I'm going to send this mouse with a bicycle helmet on. All right? And he's going to be going at about 40 meters per second, 90 miles an hour, towards this elephant. And there's going to be a completely elastic collision. The mouse is going to be okay. We've checked with the Humane Society. No animals were harmed in this physics experiment whatsoever. But M1 is my mouse, And in both and we're going to look at two situations. First one, we're going to launch the mouse towards the elephant. He's ready to go. He's got a little helmet on. Okay, and the elephant's standing there at center ice. This is, hockey fans love this stuff. All right, and in both cases, but the elephant's not moving, so I can ignore this half of this equation. I want to see what the final velocity of the mouse is going to be, and I want to see what the final velocity of the elephant is going to be. Now, what this means when you have double inequality signs, this means that anytime M1 and M2 are together, just treat M1 as if it's 0. It doesn't. In other words, if I have a mouse of like the bullet, like 30 grams, and I've got an elephant of 500 kilograms or whatever they're going to be, I don't know, bigger than that. Big. Then we'll just treat M1 as if it's 0. So, and we're going to ignore this half. So if M1 is 0, if I can just cross out M1, I can find the velocity of this mouse is negative M2, the mass of the elephant, divided by the mass of the elephant. What's negative M2 divided by M2? Negative 1. So his velocity is going to be negative 1 times, let's say V01. We sent him in there was 40 meters per second. So his final velocity coming out will be negative 40 meters per second. Right? Hits the elephant, fires right back. Okay? Now, what's the elephant's velocity going to be? Again, we just let M1 be 0. Anytime you got 0 in the numerator, what happens? No, he's in the numerator. This is 0. So what's the elephant do? Nothing. He stays right there. But the energy in the system is conserved. The momentum is conserved because the mouse goes careening towards him, boom, and bounces back with the same velocity, and the elephant does not move. That's kind of strange. Let's flip it around. Now it's the elephant's turn. Now we got the crowd going wild. Okay? We're going to we want to leave these guys the same. Now the elephant is going to be, mass 1 is going to be much, much bigger than mass 2. So now we're going to let mass 2 be the one close to 0. All right. So now M2 is close to 0. So on this one, I cross out this guy, cross out this guy. So the elephant is heading towards the mouse, and his final velocity, the mouse is just sitting there. The final velocity of the elephant then is, he doesn't change at all. He just keeps going. 40 meters per second. Oh, we're not going to send him that fast. We're just going to send him V1 initial. We'll send the elephant at about 5 meters per second because he's not, we don't want to hurt the mouse. Okay? And then his final velocity is 5 meters per second. But then something kind of strange happens. Something kind of strange happens. The velocity of the mouse, who gets smacked into. 2 times M1 over M1, we ignore the M2 part. Whoa, the velocity of the mouse now is 2M1 divided by M1 is 2. So the velocity of the mouse is 10 meters per second. So the elephant doesn't slow down a bit, but boom, he takes off. Now, you might be going, wait a minute. How can you say, remember, we're doing it with these conditions. How can you say then, with that first one, that P naught is equal to P final when he's going in completely the opposite direction, right? You smacked into it with the opposite direction. I can say that because in our system, this mass was so much smaller than M2 that we basically had this. that mouse has very little momentum. He hardly has any compared to the whole overall system. Okay? He's so small. And then you might be going, well, wait a minute. Now, what about this one, where the mouse is going twice as fast? Well, the momentum's conserved because, again, he's so small, this doesn't add to the system at all. It's just this one. And these two are still the same mass, so linear momentum's conserved. The first one, yeah, it's kind of one of those, when physicists start taking limits and getting really, really small, we just start making up answers. No, kidding, but that's basically what happens. We don't make up the answer, but that's physically what's going on. All right, let's talk about, real quick, center of mass. And center of mass is one of the easier things you're going to learn about, but it's one of the most important things that you'll learn about. And basically, the reason center of mass is important is because, let's look at two examples. One, let's look at a fireworks. Shoot a firework up like this, boom, it goes into its pretty carnation explosion, like that. Now, linear momentum's conserved here. All these little bitty vectors, all these little sparks, all these pretty little things, I mean, there's some energy lost and stuff, but for the most part, they all add up to be whatever the initial thing was going in, okay, if we added them all up. But the center of mass stays on the same trajectory. Same thing happens if you take a plate. Let's take a piece of, let's say we go nuts in Pottery Barn Kids. That's the silliest story I've ever seen. That's like, come on, get over yourself, people. But anyway, I'm sorry if any of you shop there, but to me it's just like, that's a little much, don't you think? But anyway, you take a piece of pottery, you take a flat plate, and you drop it on the concrete out there. What happens? It shatters in all different directions. Okay? And that's the same thing, but again, its momentum is conserved, because when I hold it and I drop it, what's its momentum in the x direction? All those things go off in the on the xy plane, right? I'm dropping it from the z direction. So its momentum in the z direction is not conserved because there's a new force I'm introducing, and that's the floor pushing up on it. It's just like when I drop the Dr. Pepper. But the momentum, while I'm holding it up here and it's falling, what's the momentum in all the x and y directions beforehand? While it's still falling, it hadn't hit the floor yet. Zero. Zero. So that plate is coming down, and then it breaks up, let's say, into three pieces like this. It shatters. One piece goes off this way. Oop, that wouldn't be. That's 1, 2, 3. So this piece goes like this. One goes flying off this way. Let's say 2 goes flying off that way, and 3 goes flying, well, let's just say straight back that way. That type of thing. Now, its center of mass does not change. Its center of mass just stays where it is. And you all said that the p beforehand in the x and y directions, the initial p beforehand was equal to 0. You're absolutely right. That's right. And its center of mass, then its velocity of its center of mass will stay the same. Will stay 0 also. Okay? So that's what we're looking at. And center of mass is where something rotates. I had some gadgets downstairs, but I forgot to bring them. So one of the best illustrations, let me see. Okay, I apologize. It's going to give me about 30 seconds here. I forgot to log in because Hal turned off my computer before I came. He didn't. I'm teasing. All right. And then I'll show you how to compute the center of mass, and it's pretty simple. Well, I've got a little slideshow on center of mass. Oops. Oh. So Jonathan, you're just going to become a permanent member of this class? Yeah. It's much more comfortable digs than that other one. The other class is in 104 Royal Hall. First of all, I always get annoyed because I try and go get, every time I try and get a cup of coffee, you always get stuck behind somebody who wants the, raspberry chipotle mocha with diet, but with whipped cream. So what's the point of getting, anyway, the sugar-free mocha with whipped cream. All right. So anyway, let me go load this thing. But that room is like huge, and the desks are even smaller than these, and they're trying to take notes, and it's just ugly. It's just ugly. Let's see, open. Oh, I got to turn on the thing, but first I want to call it up, make sure we've got it. Okay. Oh, I forgot to turn this on. Hold on one second.
I'm sorry, I was just looking like.
I'm going to turn it up a little bit. Projector on. Did that come on? Oh, it's trying to. It's trying to. Okay, you ready? Here you go. Here's one of the best illustrations of watching the center mass of a wrench as it flies through the air.
You can dodge the wrench, you can dodge a ball. Any other questions?
Okay. Well, anyway, so if you can dodge a wrench, you can dodge a ball, because its center of mass will stay the same, just like a ball. If you keep its eye on the center of mass, it'll keep going. All right. Okay, so the center of mass, well, this is all from the physics of sport thing. But so I wanted to get to some of the other. Okay, where would the center of mass of this bat be? What? Probably closer to where it says like Genuine or yeah, where it says Louisville Slugger. By the way, due to global warming, what are all the bats made out of now? What? They're made in the major leagues. I don't deal with college or any of that. Ping. There's no such thing as ping. It's a crack of a bat. Anyway, they're all made out of maple now. Okay. They used to be made out of ash, out of hard ash, but our ash forests are disappearing. Anyway, so and where would the center mass of this thing be? Of the tennis racket? Probably right here, I would think. Well, but except I kind of like what McKenna's think, because there seems to be a lot of mass down here, too. And it's wherever you can. The best place to put the center of mass is where you can get the most torque when you're swinging, too. Okay, irregularly shaped objects, yada, 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 yada. Okay, here's kind of a cool thing. The geometrical method of showing the center of mass. What you do is you'd hang this from one corner. You hang the object from one corner and you just run A down here like this. And then you hang it from another and leave your line there for A. And then you hang from another corner and run B down. And where these two lines intersect, that's your center of mass. Okay? That'd be your center of mass. That's the geometric method of finding the center of mass. We're going to, of course, use this is algebra-based physics. So I'm going to show you the algebraic way of doing it here in a minute. All right? And now, I've got these guys down in my office. I forgot to bring them in. Okay? The center of mass of that one object is right there. Where would the center of mass of this boomerang-looking thing be, do you think? Like right over here? Could it be here? Does the center of mass have to lie on the object? No. And when I say donut, you'll go, oh yeah. Because if I throw a donut, or one of those frisbees that are made out of the ring that are hollow in the middle, the center of mass is right there in the center of the ring, and it just follows along when you throw it. So the center of mass of this thing is actually right around in here. Okay, and the center of mass of this thing looks like it'd be more over here by the blob. Okay. Well, anyway, there it is. There's the center of mass like the boomerang. All right. So, and one of the things about center of mass too is how much force is required to do so. Any of you run track in high school? Any tracksters? Okay. You look like a distance man. You weren't a high jumper, were you? Pole vault. Oh, same thing. Okay, you were a high jumper. All right. You did the Fosbury. Was it Fosbury or Fosberg flop? Yeah, the Fosbury flop. The reason you do that is because if, say you got to get over this bar, the way that they used to teach it was you'd run up and kind of throw yourself like this. You get in your chest, which is basically where your center of mass is, if you're male, is up here. What the flop did was, and so you got to get your center of mass over the bar. What the flop does when they come in backwards, since he arcs his back like the boomerang, his center of mass is down here. That's why it works. So your center of mass is actually going underneath the bar, but your body's flipping over it. So that's why the Fosbury flop worked. And we've got more. I should have brought it in for pole vaulters when you're doing the pole vault. When we went from bamboo to aluminum or to fiberglass poles, went from like 14, 15 feet to boom, 19 feet, 20 feet. You know, and then Sergei Bubka, I think from Russia, still holds all the world records. Doping. Anyway, all right. But I couldn't catch it back then. Anyway, no, I don't know. He might have been. All right. But, there's one other thing. And also, any of you take when you were kids, had to take the presidential fitness test, all that stuff? What did they make the young ladies do instead of pull-ups? The flex arm hang, okay? All right, we do the same thing in the Marine Corps. It's because young ladies, their center of mass is much lower than men, and it's also a little bit longer. And so push-ups or pull-ups, push-ups too, standard push-ups, are very difficult for them to do, and so are pull-ups. All right, but they can hang there. They can hang there, and so that's why in the Marine Corps we don't make them do pull-ups. Even though I've seen some young ladies that can do pull-ups. They're scary, but I've seen them. Anyway, all right. So let's figure out how to find the center mass since it's the last thing we're doing. All right. But if you had a problem, let's say you had a problem where it said a dish with a explosive charge is sitting on the floor, and all of a sudden it blew up into 3 pieces. Boom. And they gave you the velocities of 2 of the pieces in their direction. Could you find the velocity of the third? Yeah, it's still going to be an algebraic nightmare, but you could find it. Because you take the sum because what's all the momentum before it blows up? 0, right? And then everything else you can. So that gives you equations to work with. All right. Let's figure out how to do center of mass. I'll just give you an example. Center of mass is very important. Also, center of gravity. It's the same thing, roughly. All we do with center of gravity is we multiply it by g. We get center of gravity. Okay. All right. We'll talk about center of gravity. Right now, we don't want to talk about torque, so that's why we're not talking about center of gravity. Let's take this example. Let's take this guy. Let's say he's 2 kilograms. Let's say he's 2 kilograms. And he's 2 meters away. 2 meters here. He's 2 kilograms. And he's 2 kilograms. Then these are all 2 meters. This is my system. I've got 4 bowling balls, 4 small bowling balls sitting like this. Where would the center of mass of this thing be, do you think? Right smack dab in the center. Okay, now, let's raise the level of pain to that question just a little bit. Let's change this and this. These are wooden bowling balls. Now let's have some lead bowling balls. 20 and 25 kilograms. Originally, you said the center of mass was right here. Now, where's the center of mass, do you think?
Up towards the 25?
Yeah. Darn tootin'. It might even be on it. It'd be right here. In other words, if this was a sheet and it had a heavy ball at this end, like it's a real thin sheet, but you had heavy weights there at the end, where would you put your finger to balance the thing? That's pretty much what you're doing when you're finding the center of mass. That's kind of the quasi-geometric method of doing it. Okay? Yeah, the center of mass would definitely move that way. So with that intuitive knowledge, to find the exact center of mass of this thing, you do it this way. When we're finding the center of mass, we're actually looking for the x component of the center of mass and the y component of the center of mass. We're going to wind up with a coordinate axis point of x and y. Okay? And the x center of mass is found this way. You go, oh, you start with, you take each mass. And let's say that this is set up this way. This is my coordinate axis system. So this is at 0, this is at 2, this is at 2 and the y, and this is at the point 2, 2 over here. And we're going to, okay, so the first thing you do is you start with this guy and you go, oh, 2 times the distance he is on the 2 kilograms times the distance he is on the x-axis. How far is he along the x-axis? 0. So it's 2 times 0. Not bad. Plus, we'll go to this guy. 2 times, how far is he along the x-axis? 2 meters. Plus, we'll go over to this guy. It doesn't matter what order you go in. What's this guy in the x-axis? 0. So we'll go 20 times 0. Mass times, so you're doing mass times distance, mass times distance, mass times distance, all the way through. 20, 0, plus 25 times 2. Divided by, now even though I've got a 2 and a 20 with multiplying by 0, I've got to put all those masses in the denominator. Okay? So I put in the denominator divided by 2 plus 20 plus 25, which equals 49. So the XCM, so the XCM, center of mass, the x coordinate part is 4 plus 54 over 49. That's about, what, 1 and 5/49 left over. That's about 1.1. So that's at the point about 1.1. So here'd be 1. So my x center of mass is located right there, roughly. Which makes sense. If this would have been 25, my x center of mass would have been right there at 1. Right? Because that would have made sense. Because symmetrically, we'd have gone, oh, yeah, this folds over its center of mass nice and symmetrical if I'd have made this 25. You see that? So it would have been right at 1. But since this is a little bit heavier, it's here at 1.1, which is at about 1.1 meters. You do the same thing with the y-coordinate. Do the same thing with the y-coordinate. The YCM would be, start with this guy. Again, 2 times 0 plus 2 times 0 plus 20 times 2 plus 25 times 2 divided by once again 49. So I wind up with 40 plus 50. What's 40 plus 50? Oh, 90. 90 divided by 49. Ooh, see, that's real close to 2, just like you all said. It'd be right up. I mean, that's real close. I don't know what it is. 1.8 roughly. It's about 1.8. So we come up, we go to here, and then we come up to about 1.8, which would be right about there. Here's my center of mass. Just exactly what you all intuitively thought. It's really easy. That's probably the easiest thing we've done all semester so far, is finding the center of mass zone.
Is that an entire line of center of mass or just the y?
Oh, that's just the y part. The y part is going across here, and the x part is going across here. Yeah. And there it is. All right. All righty. That's it for today. I forgot to make up a quiz. I'm sorry if you came just to take it, but you know, it's okay. Robin's giving me a free pass on that, so I feel better. All right, that's good.